Water erosion and its types. What is water erosion? Water erosion is the erosion of soil caused by water. Water acts as the main agent to dislodge and transport the eroded soil particles from one location to another location. We have discussed soil erosion in the previous chapters. Soil erosion is the process of detachment, transportation and deposition of soil particles. When the flowing water does not have sufficient kinetic energy, the soil particles get deposited to another location. Water erosion is the removal of soil by water, mainly by rainfall and runoff. The rainfall has tremendous amount of kinetic energy. It has the ability to detach the soil particles, which are consequently carried away by runoff. It involves soil particles moving with flowing water, settling into lower areas. Or when the kinetic energy of flowing water is not sufficient, the soil particles may get settled. Managing and preventing water erosion is crucial. We may have to adopt mechanical measures in order to reduce the erosion caused by water. We may adopt terracing, bunding, or we may also adopt check dams in order to check the water erosion. What are the causes? It is mainly caused by rainfall. It can also be caused by snow melt, runoff and poor irrigation management. Types of water erosion. Water erosion is initiated by impact of raindrops. We call that erosion as splash erosion. It is the erosion which is caused by raindrop impacts. It initiates the movement of soil. Higher the intensity of rainfall, higher is the rate of detachment of soil particles. Once the soil particles get detached, they are carried away by flowing water. Sheet-like erosion that occurs between small depressions in the landscape is called inter-rill erosion. Rill erosion. When small shallow channels in the soil are formed by concentrated runoff, that erosion is called rill erosion. If these erosions are not checked, the size of rills may become gradually larger and they develop into gullies. So gully erosion is the development of deeper and wider channels in the landscape due to flowing water. Stream bank erosion. Gradual wearing away of river or stream banks by water is called stream bank erosion. When the stream takes a turn, the impact of water is higher on the banks. And when this flowing water hits the bank, there is every chance that high amount of erosion can be caused to the stream banks. Tunnel erosion. This erosion usually occurs beneath the soil surface and creates tunnels or subsurface channels. Let us learn splash erosion. Splash erosion is the erosion caused by raindrops. When raindrops hit the soil particles get detached and they get splashed in all the directions. Soil particles are displaced from their original positions. As I discussed before, if the intensity is high, the detachment rate will be higher. This process involves raindrop impact, soil particle splash and formation of craters. Clay particles are somewhat difficult to detach compared to sand particles. But once the clay particles are detached, they can be easily carried away by flowing water. Raindrops build momentum before releasing energy as a splash, forming craters of varying shapes and sizes. these raindrops will acquire tremendous amount of kinetic energy. K is equal to half mv square. So this kinetic energy is used up in detaching the soil particles, and it also creates craters of various shapes and sizes. Crater depth depends on velocity of the raindrop. Even size of the raindrop has an influence on the depth of crater. So size and shape depends on the raindrops. Depth of crater caused by splash. Mathematical relationships have been developed to estimate the characteristics of crater. D equal to K R rho V square raised to 1 by 3, where D is the crater depth in centimeters. K is a constant, R is the radius of raindrop, rho is the density of raindrop, V is the velocity of raindrop. So if we enter the values of K, R, rho and V, we may be able to estimate the depth of craters using this mathematical relationship. Now, volume and area of crater caused by splash. Volume of crater caused by splash can be mathematically expressed as V equal to 1 by 3 pi d square, in brackets in the numerator 3d square plus 12d square divided by 8d minus d. Area of crater caused by splash is A equal to pi in brackets d square divided by 4 plus d square, where small d is the diameter of crater and capital D is the depth of crater. Crater volume. Volume of crater which is caused by the raindrop based on the kinetic energy and bulk density can be given by V equal to rho d raised to half, rho b raised to half divided by rho d plus rho b multiplied by E by 2 Rho d is the raindrop density. Phi is the flow stress of soil. Rho b is the bulk density. The size of craters increases linearly with increase in raindrop energy. Once rainfall initiates, small rills start forming on the land. The runoff between these rills is called sheet erosion or inter-rill erosion. It includes detachment of soil by raindrops, transport by shallow sheet flow, and ultimately this water gets delivered into the rill channels. This type of erosion is mainly caused by shallow flow and is the most common form of soil erosion. It may not look threatening at first, but it accounts for about 70% of total soil erosion occurring alongside splash erosion. Inter-rill erosion depends on particle detachment, rainfall intensity, and field slope. Inter-rill detachment rate. You can determine the inter-rill detachment rate using this equation. Di is equal to Ki multiplied by I multiplied by S. Di is the inter-rill detachment rate. Ki is the rate of inter-rill erodibility. I is the rainfall intensity, and S is the slope factor. S can be estimated using this equation. S equal to 1.05 minus 0.85 exponential minus 4 sin theta, where theta is the slope angle. Rill erosion. Rill erosion happens in small channels or rills because of concentrated flow. In area where flow is allowed to get concentrated at certain points, rills start forming, and if these rills are ignored, they will gradually develop into gullies. Rill erosion is the second most common form of erosion. Rills start enlarging due to flowing water and soil particles along their beds. They can be erased by tillage, but they will cause significant erosion, especially during heavy rains. Rill erosion depends on soil erodibility, runoff capacity, and water flow shear. Gully erosion. Gully erosion creates V or U-shaped channels which are at least 0.3 meters wide and deep. Gullies form because of concentrated flow, just like rills. The concentrated runoff converges into low points. It's called concentrated flow erosion. On uneven fields, runoff starts getting collected into natural swavels, forming channelized flow. Growing gullies will remove the soil and transport these sediments. There are two types of gullies. One is ephemeral and other is permanent. Ephemeral gullies are temporary gullies. They can be erased by certain tillage practices, whereas these permanent gullies are too large to be easily erased by tillage. It is difficult to restore the land into its original state if permanent gullies have formed. That's why they are called permanent gullies. The damage is too strong now. Ephemeral and permanent gullies. Ephemeral gullies can be fixed with routine tillage, whereas permanent gullies are too big for this and they need costly reclamation. Right? So ephemeral gullies may reappear if they are not controlled. By filling the gullies with soil from nearby fields, you can reduce the topsoil depth. See, for controlling gully erosion, we may adopt several measures. Okay, you will be learning about some of these measures like diversion drains, temporary and permanent dams in the subsequent chapters. But by maintaining vegetation, gully formation can be prevented. Overall, preventing gully erosion through proper land management practices is essential to maintain soil health and prevent downstream sedimentation. So it all started with splash erosion caused by raindrops, then inter-rill erosion, that is thin sheet of water will flow in between the rills. This is called inter-rill erosion. Then water is delivered into small rills. These rills may get enlarged and form gullies. So what are the factors that affect gully erosion? It is mainly influenced by two factors: the shear stress of flowing water and the critical shear stress of soil. Flowing water's shear stress causes the detachment of channel bed as well as the sides. Now, what measure can we adopt in order to reduce the formation of gullies? Grassed waterways. Yes, they have the ability to reduce gully formation. Bare and freshly plowed soils are the most susceptible to gully erosion as they have the lowest critical shear stress. The critical shear stress of soil depends on various factors including texture, bulk density, clay content, tillage practices, presence of plant roots, residue cover and slope of the soil. Tunnel erosion. It is the erosion that is caused beneath the top layer. Tunnel erosion or pipe erosion occurs underground and it is common in arid and semi-arid regions. It often affects those soils with erodible and sodic B horizons but stable A horizons. This erosion is initiated by runoff in channels, natural cracks or animal burrows infiltrating and moving through dispersible subsoil layers. Tunnel erosion has the potential to alter the landscape and hydrology. Next. It begins when runoff infiltrates into this dispersible subsoil layers through channels, cracks, or animal burrows, and it starts becoming bigger and bigger. Tunnel affected soil surfaces are often stabilized by plant roots while the subsoil remains easily erodible. As the tunnels expand, there is a chance that the surface can collapse. The surface can collapse and it will form potholes and gullies. Reclamation strategies include deep ripping, contouring, tree and deep-rooted grass vegetation, soil surface repacking, and runoff diversion. Stream bank erosion. It is the collapse of stream, creek, or river banks caused by runoff erosion from upland fields. There is a strong impact of flowing water where the stream takes a turn. In those areas, the banks are more susceptible to erosion. It leads to pedestals with vertical cuts along stream banks. Factors like intensive farming, grazing, traffic near water, and lack of riparian buffers accelerates stream bank erosion. So what are the control measures that can be used for reducing or preventing stream bank erosion? Well, they include planting grasses and trees, using engineering structures to manage the runoff. These measures will help in prevention of further stream bank erosion, and it will also protect the quality of water. Processes of water erosion. So it involves 3 steps: detachment, transportation, and deposition. It starts with raindrops hitting the soil and detaching the soil particles, followed by their transport. These detached soil particles will form surface seals, blocking the soil pores, reducing infiltration and causing runoff. This is also an important point. The soil particles that got detached by the rainfall, they will block the soil pores and thereby reduce the infiltration. And if the infiltration is reduced, it will cause increase in runoff. At a micro scale, a single raindrop can initiate erosion by weakening the aggregates of soil. These erosion processes occur sequentially during intense rainstorms. Which are the factors that affect water erosion? Precipitation, vegetation cover, topography, and soil properties. Precipitation. See, the amount, intensity, and frequency of rainfall events will significantly influence the potential for water erosion. If the intensity is high, the detachment and transportation rate will also be high. Vegetative cover. Vegetation stabilizes soil. It will also increase the organic matter of soil, and definitely it can reduce the impact of raindrops on the soil surface. How will topography affect water erosion? The shape, steepness of the land can impact erosion rates, with steeper slopes being more susceptible to erosion. Soil properties. See, texture, structure, erodibility can affect the vulnerability to erosion. Loose, poorly structured soils are more prone to erosion compared to those soils which are stable and well structured. Now, let us discuss rainfall erosivity. Erosion is a function of rainfall erosivity and soil erodibility. We will briefly discuss these two, rainfall erosivity and erodibility, in this chapter, and then we will be studying them in detail in the subsequent chapters. In the subsequent chapters, we will also be discussing the equations which can be used for calculating erosivity. We will also be solving problems related to that. Rainfall erosivity is the inherent ability of rain to cause soil erosion, and understanding it is crucial for erosion control. It is the primary factor. Now, which are the properties which influence the erosivity? The rainfall amount, intensity, terminal velocity, drop size and drop size distribution. All these factors have a strong influence on erosivity, the ability of rainfall to cause erosion. Rainfall erosivity and its impact differ across climatic regions, even with the same amount of rainfall depending on intensity and soil conditions. The rainfall could be same, but depending on intensity and conditions, the impact will be different across various climatic regions. Rainfall erosivity knowledge is essential for estimating the soil erosion rate and designing effective erosion control practices. Rainfall intensity is the most critical factor determining erosion levels. High rainfall amounts combined with high intensity will result in significant erosion. Intense storms may be brief, but they have the ability to cause substantial erosion. Total intensity of a storm is determined by intensity of individual raindrops, which depends on raindrop size and the terminal velocity. Higher the velocity, higher will be the kinetic energy of these raindrops. And finally, the total intensity of storm will be quite high. Measuring the kinetic energy of raindrops is quite challenging, but sensors are available. These electronic sensors can be used for direct measurement. It converts the sound waves which are produced by the raindrop impacts into measurable data. Kinetic energy of falling raindrops. It is possible to estimate the kinetic energy of rainfall if the mass of falling drop and velocity of fall is known to us. Once you substitute these values, you can calculate the kinetic energy of rainfall. Kinetic energy of rainfall. Now this equation is given by Wishmer and Smith, 1978. E equal to 0.119 plus 0.0873 log of I. Now, if the intensity of rainfall is less than 76 millimeters per hour, less than or equal to 76 millimeter per hour, then we are supposed to use the first equation to calculate the kinetic energy. In the first equation, you can see if we substitute the value of intensity, we will get the kinetic energy. In case the intensity is greater than 76 millimeter per hour, we just have to assume that the kinetic energy will be equal to 0.283. Here the kinetic energy is in megajoules per hectare millimeter of rainfall, and I is the rainfall intensity, millimeter per hectare. Runoff. Runoff is the water from rainfall, snow melt or irrigation which flows off the field and ultimately joins into streams or rivers or lakes after soil absorption, pore filling, surface storage and accumulation. So once all these retentions have been fulfilled, the resulting flowing water will join the streams. So runoff is equal to input minus output. Input is rainfall, snowmelt, irrigation water, and output includes infiltration, evaporation, interception by rainfall interception by canopy, water absorption, transpiration and surface detention. So runoff will be input minus output. Resulting flow will be runoff. So once all this absorption, pore filling, surface storage, accumulation is fulfilled, the water that flows is called runoff. Okay, next. Runoff erosivity. Now note that rainfall has more erosive power than runoff. Runoff erosivity is the ability of runoff to cause soil erosion. Rainfall will directly impact the surface, it detaches and splashes the soil particles. And then these soil particles are carried away by runoff. Runoff has ability to contribute significantly to erosion, but the initial impact of raindrop is often more erosive because it is responsible for directly loosening and dislodging the soil particles. Why do we need to estimate runoff? We need to estimate runoff in order to design erosion control structures such as ponds, terraces or channels. In order to create conservation buffers, we need data of runoff. These conservation buffers may include grass barriers, filter strips or riparian buffers. In order to estimate the sediment and chemical runoff, we need the information on runoff. And for safely managing runoff in channels and waterways, we need runoff data. Then only we can plan and design some structures or adopt certain vegetative measures. Which are the factors that affect runoff? Runoff rate and volume depends on several factors. It depends on topography, soil conditions and vegetation. Impermeable surfaces means the surfaces which has almost zero infiltration. So in those areas there will be heavy runoff. All the rainfall will be converted into runoff. There will be no storage as the surface is impermeable. So impermeable surfaces lead to complete runoff, while natural conditions involve interception, infiltration and other factors. So how can we estimate runoff? We can estimate runoff using several methods. We may use mathematical equations to estimate the runoff, and these equations will generally include all these factors. Now, rainfall in natural environment is divided into various pathways, including plant interception, infiltration, evaporation, surface accumulation and eventual runoff. So the method that will be used for computing runoff will take into consideration all these factors for calculating the runoff. Time of concentration. Let us try and understand what time of concentration is. It is the time that runoff takes to flow from the farthest point in a watershed to the outlet. A watershed has one outlet. Now the time that is taken by the flow to reach from the farthest point to the outlet, this time is called time of concentration. Runoff is quickest when it rains throughout the whole watershed. Surface features like depressions can affect time of concentrations, which impacts the runoff rate. Urban development with impervious surfaces will have lesser time of concentration and increased peak discharge rates. Yes, if the surfaces are impervious, it will take less time to attain the peak discharge, and the time of concentration will be quite less. The water will quickly reach the outlet point of the watershed. What are the factors that influence the time of concentration? Surface roughness, slope of watershed, size of watershed and characteristics of the channels present in the watershed. If the surface is smooth, the time of concentration will be less. But if the obstacles are present, then it will take longer for the runoff to reach from the farthest end to the outlet of the watershed. Obstacles may include vegetation and terrain features which can slow down the runoff. Conservation buffers in watersheds decrease the slope and thereby it will extend the water travel time. While channels which are smoother will have increased runoff. Bigger watersheds have more contributing area, but it will take a long time for runoff to reach the outlet. In small watersheds, peak runoff is obtained quickly. Those channels which are longer and smoother will have reduced travel time. Straight channels will speed up the runoff, while those channels which are meandering will slow down the runoff. So these are the factors which influence the time of concentration. Runoff volume. Runoff volume can be computed using several methods. Here we will be using the runoff curve number method. It's an empirical approach for various soil and surface conditions. Q, which is the depth of runoff, can be calculated using this mathematical equation. Amount of daily rainfall minus initial abstraction whole squared divided by amount of daily rainfall minus initial abstraction plus the retention parameter. If we substitute initial abstraction equal to 0.2 s, then the equation will take this form. R day minus 0.2 s whole square divided by R day plus 0.8 s. S can be calculated using this equation. S is equal to 25400 divided by Cn, the curve number, minus 254. S represents the variations in soil conditions, land use and moisture content. Cn value decreases with more vegetation, ranging from bare soils, which will have higher Cn number, to dense vegetation cover, which will have lower Cn number. Okay, Cn is curve number. So, soils are classified into various hydrologic groups A, B, C, D based on runoff potential, which are determined by factors like infiltration capacity, drainage and impermeable layers. So, Cn values are available in tables. Let us solve one example to understand this runoff calculation using curve number method. So here is the example. Calculate the daily runoff for a watershed having an area of 3 km square and the amount of daily rainfall, average daily rainfall in this area is 10 millimeters per day. Okay. The watershed is divided into these land uses. It includes bare soil, impervious area and forest area. The hydrologic soil group is B for all the land uses. So what is the total area? The total area is 3 km square, is divided into 3 land use: bare soil, impervious area and forest area. So this is the allocation of area. Bare soil comprises of 0.75 bare soil occupies 0.75 km square out of 3 km square. Impervious area occupies 0.250 km square and forest area is more compared to bare soil and impervious area. Forest area is 2 km square. Now these values of Cn are taken from the table. 86 for bare soil. If there was vegetation, the curve number would be less. Impervious area 98. See the increase in curve number. In impervious areas, there will be insignificant amount of infiltration. Most of the rainfall will be converted into runoff, and therefore we are saying higher value of curve number. Forest, it has the tendency to hold the soil and to check the runoff, and therefore the curve number is less. Now let us try and calculate the daily runoff using the curve number method. Step 1. Computation of area weighted average curve number. So this data is already given to us, land use, area and curve number. We have to find the weighted curve number and we will take its average. So when 86 is multiplied by 0.750, I get the weighted curve number for bare soil. When 98 is multiplied by 0.250, I will get weighted curve number as 24.5 for impervious area in this watershed. In case of forest, the curve number is 55, which when multiplied by 2 gives us 110. Area weighted average curve number is A1 multiplied by Cn1 plus A2 multiplied by Cn2 plus A3 multiplied by Cn3 divided by the total area. We have three types of land use here. Okay, so and I will substitute area of each land use. So 64.5 plus 24.5 plus 110 divided by the total area of watershed, which is 3 kilometers square. So we will get area weighted average Cn, which is equal to 66.33. So this is the first step. Second step includes computation of S, which is the retention parameter. S is equal to 25400 divided by Cn minus 254. So we have already calculated the average Cn, which is 66.33 for this watershed. When I substitute the value of Cn in this equation, I will get the value of S, which is equal to 128.93. Step 3, computation of runoff depth, RD, which is daily rainfall. This data is available with us. It is 10 millimeters per day. We just calculated the value of S. Now let us substitute these values into this equation. So 10 minus 0.2 multiplied by 128.93 divided by 10 plus 0.8 multiplied by 128.93. We will get the runoff depth equal to 2.20 millimeters. The runoff volume can be computed by multiplying this with the area of watershed and changing the units appropriately. So area was given to us in kilometers. So here it is 3 kilometers square multiplied by 1000 meter whole square divided by 1 kilometer square multiplied by 0.0022. So I am doing all this to convert it into appropriate units. I am converting everything into meters. So I will get the runoff volume in meter cube. So when I multiply the runoff depth by the area of watershed and convert into meter cube, the answer is Q is equal to 6,600 cubic meters. So this is the runoff volume. Thank you.